Hi, welcome to today's talk on fluids in motion. What are we learning? We're going to learn about the equation of continuity, we're going to review conservation of energy, and we're going to look at Bernoulli's equation. So there's two different types of fluid flow, streamline or laminar flow, and then there's turbulent. With streamline, every particle moves along exactly at the same smooth path as the previous. These streamlines don't cross. And the streamlines tell us the direction of the fluid flow. Here's another example. Let's say smoke rising from incense or a candle. At the bottom, we have streamline or laminar flow. And notice what happens up here. This is what we'll call turbulent flow. And above a certain velocity, or under conditions that can cause an abrupt change in velocity, the fluid flow becomes very irregular. These are sometimes called eddy currents. And they're a characteristic of turbulent flow, as we can see here. When we look at fluid motion, we can understand it a little bit better if we consider the idea of an ideal fluid. First, the fluid is non-viscous, which means that there's no internal friction force between the adjacent layers. The fluid is incompressible. This is telling us that the density is going to remain constant. The fluid motion is steady, that the velocity, the density, and the pressure at each point in the fluid doesn't change with time, and that the fluid moves without turbulence. This picture shows fluid flowing through a pipe of non-uniform size. The particles in the fluid, they move along streamlines, steady state flow. In some small amount of time, delta t, the fluid entering the bottom end of the pipe moves a distance delta x, or our displacement, which will be the velocity times that very small amount of time. If A1 is the cross-sectional area of this region here, then the mass contained down here at the bottom in this blue region is given by this equation, delta M1 equals rho 1 area 1 times delta x1. Substituting delta x in, we get rho a, the density, times the area of 1, the velocity down here, and this small amount of time. Now, don't worry a whole lot about this derivation. Just wanted to show you where this came from. Same thing will be true up here at area 2. Now, mass is conserved, so we can equate both of these things together. Since the density is the same, rho cancels out. And that brings us to our equation of continuity. The area 1 times the velocity 1 down here is equal to area 2 times the velocity 2 up here. We will call the area times the velocity the flow rate. Let's look at an example of what might come from this equation of continuity. We've probably seen this. Notice that when the water is leaving up here, it has a larger area, and we know that the velocity is increasing as it falls down. So as the velocity increases down here, the area has to get smaller because this flow rate is a constant. So the flow rate up here with a larger area, smaller velocity, will equal the flow rate down here with a smaller area and a smaller velocity. Let's do a quick review of our conservation of energy, looking at kinetic energy and gravitational potential energy. First, kinetic energy is the energy of motion. It is 1/2 the mass times the velocity squared. Our units are a joule. Remember, energy is a scalar quantity. Our second type of mechanical energy is gravitational potential energy, the energy of position. and that we will calculate as the mass times free fall acceleration times y, or h. It's also in joules, and it's also a scalar quantity. Let's take a look at a quick example of the conservation of energy, a very simple one. Let's say we have to save somebody from a burning building. Don't worry, we've got firefighters who are going to save her at the end. She starts out with potential energy, her mass times free fall acceleration times the height. Let's say she starts from 10 meters, she's 100 kilograms. Let's just use 10 meters per second. She has a potential energy of 10,000 joules. At this point, she has a kinetic energy of 0. So the total energy is 10,000 joules. This will be constant throughout her fall. The total mechanical energy is a kinetic energy plus a potential energy. Obviously, right now, it is 10,000 joules. As she falls, she starts to lose her potential energy and gaining kinetic energy. Notice that it still adds up to be 10,000 joules. And halfway down, she has half the potential energy she had before, but she has gained kinetic energy. Notice they still add up to be 10,000 joules. Finally, right before she hits, and saved by the trampoline here, she has a kinetic energy of 10,000 joules and 0 joules of potential energy. We're not looking at the work done by any friction or air resistance in this case. Now, Bernoulli's equation is a consequence of energy conservation, and we're going to apply it to an ideal fluid. So as a fluid moves through a pipe of varying cross sections and elevations, the pressure changes along the pipe. Now, the work done on this lower end of the fluid is going to be force times our displacement. Replacing force with pressure times area, and then we have area times this delta x. That is volume. So we have pressure times volume. We can do the same thing up here at the top, but now the work done is negative because the force is in the opposite direction of the displacement. The work done will be the change in mechanical energy. The change in mechanical energy will be the change in kinetic energy, the change in potential energy, replacing what we found up here for work, and then expanding this to our equations for the kinetic energy and the potential energy. The volumes are the same. Divide through by volumes, and these masses all become density. Density, density, density. This is Bernoulli's equation, and notice what this is saying. This is saying that the pressure plus this, which represents our kinetic energy, and this part, which represents our gravitational potential energy, is constant. One aspect of this is that when we have a lower velocity, we have a higher pressure. If we have a higher velocity, we have a lower pressure. Another way to show that is with a Venturi tube. The velocity in the middle here will be lower than at the two sides. So the pressure is lower, the fluid is higher. This is unlike what we've seen before because the pressure in this column and this column and this column are different. Let's summarize what we know. First, we have the equation of continuity. Area times the velocity of a fluid in a tube is constant. It's the flow rate. It remains constant. Then we have Bernoulli's equation, which tells us the pressure added to the kinetic energy and to the potential energy of that fluid. That's a constant throughout that fluid. All right, thank you for listening. Complete your Cornell notes, rewind, and review as necessary.